Thank you very much for the kind introduction. Okay, so my name is Kei Matsushima from the University of Tokyo. So I want to start my talk with the introduction of my talk. So the motivation of this talk is the anomalous and exotic wave phenomena in the time harmonic wave systems. For example, the negative effective parameters in the metamaterials and invisibility cloaking and bound state in the continuum and non-Hermitian degeneracy and so on. And in this talk, I want to introduce the concept of the inverse design approach. For example, you can see this figure. So in this figure, we have an incident wave, and also we have a scatterer in the background medium. In this system, we can compute the scattering of the incident wave for the given scatterers. But what we want to do is the inverse process. So we want to find a shape or topology of the scatterer that achieves the desired given functionality or given scattering property. So this is the concept of the inverse design approach. And this is realized by using the structural or design optimization. In this talk, I want to introduce some inversely designed wave systems. So the first one is the omnidirectional acoustic cloaking with local resonant sonic material. And the second one is the unidirectional cloaking with parity-time symmetry. And the last one is the bound state in the continuum in a periodic waveguide system. Okay, now let's begin the first one, the omnidirectional invisibility. Maybe you are familiar with the invisibility cloaking, but I want to explain about the basic concept. And invisibility cloaking is one of the most anomalous or exotic phenomena in optics or acoustics. For example, we have an object in the background medium, and we have an incident light. Of course, the object scatters the incident light, so we can observe the object. But if we can design an appropriate medium or appropriate object that covers the scatterer, then we can circumvent the light around the object, and the object is perfectly invisible. So this is the concept of the invisibility cloaking. Okay, so the first concept of the cloaking is proposed by Professor Pendley, which is called the transformation-based cloaking. So in this two-dimensional system, we have a cylindrical object like this, and we design a donut-like shape around the cylinder, and the donut object is spatially varying and anisotropic material, and this to achieve the invisibility cloaking, they propose that theoretically they propose that this material distribution realizes the perfect cloaking. And this cloaking is frequency independent, so which means that the cloaking works for all frequencies. And also, the shape is perfectly symmetric, so this cloaking is omnidirectional. So the cloaking works for all incident direction. But the problem is that this cloaking is low feasibility, so that this kind of spatially varying or anisotropic material distribution cannot be realized by using a standard material. So this is the biggest problem of the transformation-based cloaking. So instead of the transformation, we use the multiple scattering-based approach. So this kind of approach is proposed by the several researchers. The first one is the acoustic cloaking, and they use the multiple rigid rods in air. So we have a cylindrical object, and we distribute the multiple rigid rods around the scatterer, and then optimize the locations of the rods, and they suppress the scattering by using the optimization algorithm. And a similar approach is done in 2015, and they optimize the radius of the rod surrounding the scatterers. So, but the problem is that so this is acoustic cloaking. So the sound speed in air is about 3,040 meters per second. So this so this cloaking this cloaking is realized by using the Bragg scattering of among the rigid scatterers. So the lattice constant of the periodic system should be larger than the half of the wavelength. So if the operating frequency is about 340 hertz, then its lattice constant should be the half meter, larger than the half meter. So this is so big, and we want to realize the low frequency acoustic cloaking by using the locally resonant sonic material. And we show that the similar system can realize also the omnidirectional acoustic cloaking. Okay, so I want to explain the model of the cloaking system. Okay, so this is a rigid circular scatterer as the previous one, and we allocate the multiple scatterers around the rigid core. And we allocate the 96 rods surrounding the rigid material core, circular core, and each rod is comprised of the lead and silicon rubber. So this is called the locally resonant sonic material. And we optimize the radius of each rod to suppress the scattering of the incident acoustic wave. Okay, we begin with the formulation of the scattering system. In this study, we consider the acoustic wave scattering. So the background medium is air and satisfied and governed by the Helmholtz equation for the sound pressure P. And in the elastic medium or solid medium, we have a Navier's equation. So the stress and the displacement U is satisfied this equation of motion. And these two partial differential equations is coupled by the boundary or interface conditions. So the stress, traction, and the displacement is continuous between the boundary or interface between the solid and fluid medium. And also we assume that the sound pressure satisfies the Sommerfeld radiation condition. So this is a boundary value problem, which we consider in this talk. Okay, so this is a typical multiple scattering problem. So we use the multiple scattering theory. So in the background acoustic medium, the sound pressure P is expanded by using the Bessel function and Funkel functions around each scatterer. And the coefficients of the expansion, so the coefficient of the Bessel function and the Funkel function B is associated by the matrix called scattering matrix S. So B is equal to S times A, like that. And we can formulate the multiple scattering equation by using this scattering matrix like this. And we solve this multiple scattering equation and solve the entire scattering problem. Okay, so now I want to show you the result of the optimization. So this is a scattering system. So we have a rigid core, and we have a lot of rods surrounding the rigid core. And the objective is to minimize the scattering intensity or scattering cross-section of the incident acoustic wave. So the objective function is the summation of the coefficient, outgoing coefficient, and we optimize the radius of each elastic rod. Okay, so this is the result of the optimization. The optimization is performed by using a standard nonlinear programming technique, and this is the optimized parameters. And this is the innermost radius, innermost rod, and this is the outermost rod. And the right figure shows the scattering cross-section versus the incident angle. And you can see that for all the incident angle, the scattering cross-section is very small compared to the bare one, so without the cloaking structure. And also this animation shows the cloaking of the designed material. And the left figure shows the case of the without cloak. So this is just a bare cylindrical material, and we have an incident wave from left, and we can see that the cylindrical object scatters the incident plane wave. But in the right figure, we have designed multiple rods, and you can see that these multiple designed rods cloak the incident plane wave. And also, this is the case of the point wave. And you can see that even for the point source wave, you can see that in the right figure, the cloaked material, the cloaking material is working for this kind of incident wave. Okay, so this is the first topic, and we move on to the second topic, so the unidirectional invisibility. So this is the opposite concept of the previous one. So the previous one is the omnidirectional invisibility, and this is unidirectional invisibility. So this is a strange concept. It is a little bit strange concept. So I want to explain about this concept a little bit. So the motivation of the concept, the unidirectional invisibility, is a fundamental reciprocity that the scattering intensity is invariant under the inversion of incident directions, regardless of the geometrical symmetry. For example, if we incident a light from left and from right, then their scattering cross-section should be equal to each other. So this is the reciprocity of the scattering system. So this means that unidirectional invisibility is impossible, but if we introduce the material loss or gain, then we can break the invariance. But to realize the cloaking, the loss and gain should be balanced to realize the invisibility. So we use the parity-time symmetry to realize the unidirectional invisibility. So the parity-time symmetry is the concept of the symmetry, and the parity symmetry or parity inversion is defined as the inversion of the coordinate system. So this shape is, so we can see that the shape is mirrored with respect to this mirror, and also we can consider the time inversion. So the time inversion of the time harmonic system is characterized by the complex conjugate of the material parameters. And also we can combine the parity inversion and time inversion to construct the parity time inversion. So this is the concept of parity time inversion. And if the system is invariant under the parity time inversion, then we can say that a system is parity time symmetric. Okay, this concept is first used by the researchers in 2015 to realize the unidirectional invisibility. They proposed to cover a cylindrical object like this by a thin film, and the film gives the continuous admittance with gain and loss. And the balanced gain and loss induces the one-way transparency or unidirectional invisibility. So this is the first example of the parity-time symmetry that realizes the unidirectional invisibility. So what we want to do is to optimize this kind of structure by using the structural optimization or design optimization. Okay, so now in summary, the objective is to design a parity-time symmetric dielectric structure with unidirectional cloaking ability by topology optimization. And we prove that a piecewise homogeneous material can realize the unidirectional invisibility. Okay, so now the formulation is written here. So in this study, we consider the two-dimensional time harmonic scattering as well as the previous one. And in this system, we consider the dielectric structure. The permittivity is denoted by epsilon, and we instance the time harmonic instant wave. So the problem is written by the transmission problem in the back. So in the background and in the scatterer, the electric field E satisfies the Helmholtz equation and also radiation condition. Okay, so before optimizing this structure, I want to explain about the reciprocity and the optical theorem for the scattering system. Okay, so when we consider the instant wave as we assume that the instant wave is a plane wave which propagates in the direction P in, and also we measure its scattering in the direction of PSC. In the two-dimensional scattering system, the scattered wave U, the total field U is written as the summation of the instant wave and the scattered wave which decays, which radiates into the infinity at the rate of order like this. And this coefficient is called the scattering amplitude or radiation or scattering pattern. And we we integrate its scattering amplitudes for all directions, and we have a scattering cross-section. So this is a definition of the scattering cross-section. And the reciprocity is written as by using this scattering amplitude. So we denote the scattering amplitude by this function. So PSC is the observation direction, and P in is the instant direction. So the reciprocity means that if we invert the observation direction and the instant direction, then the scattering amplitudes are equal. And this is the reciprocity. And we have another important theorem, which is called optical theorem. If the medium has no gain or loss, then so this optical theorem can be written in the two-dimensional system as this. So the scattering cross-section is written as the imaginary part of the scattering amplitude for when the observation direction and the instant direction are the same. And by combining this optical theorem and the reciprocity theorem, we have this equation, this relation. So the scattering cross-section of the minus P in is equal to the scattering cross-section of P in. So if we invert the instant direction, then their scattering cross-section must be the same. So this is the fundamental property of the scattering cross-section. But this means that if we have a gain or loss in the scattering system, then we can break this scattering symmetry and we can realize the unidirectional scattering cross-section. Okay, so I want to show the model of the parity-time symmetric cloaking system. Okay, in this example, we consider the perfect electric conductor, as you can see in this figure, and we design the shape of the parity-time dielectric structure like this. So in the left part of the figure, we allocate the lossy medium. So the imaginary part of the permittivity is negative, which means that the material is lossy. And in the right part, we have a symmetric structure. So the material has gain, and its permittivity has a positive imaginary part. And then we instance the plane wave from left, and we optimize the parity-time structure so that this plane wave experience the minimized cross-section. Okay, so to this end, we use the topology optimization. Okay, so I'm not going into details about the algorithm of the topology optimization, but in this study, we use the algorithm called the level set method. In the level set method, we define a scalar varied function phi which is called level set function. And this level set function defines the distribution of the material. For example, if the level set function is positive, then the medium is empty. And if the level set function is negative, then the medium is filled with material. So this is called level set function. And we optimize this level set function by using this partial differential equation. And we have an optimized shape for the given objective function. Okay, so this is the result of the optimization. And the left figure shows the convergence history of the objective function. So the horizontal axis is the optimization step, and the vertical axis is the objective function, which is the scattering cross-section. And the right figure shows the optimized shape. And so the blue color represents the lossy medium, and the red material indicates the gain material. And also this is the animation of the scattering, and for the optimized system, and we give an instant wave from left and right, and you can see that in the case of the left instant case, you can see that this system achieves the almost perfect cloaking. On the other hand, in the right case, if the instant wave is given from the right direction, then you can see that the system experiences a lot of scattering. Okay, so this is the second case.
So,
and the last.
Sorry to interrupt. Just to remind you, we have about 5 to 10 minutes left. So
Okay, thank you very much.
Thank you very much. Thank you.
Okay, so I don't have enough time. So the last one is a bound state in the continuum. Okay, so the motivation of this topic is so wave propagation along periodic obstacles in the two-dimensional space, and we have a periodic obstacles, as you can see in this figure. And in this system, we have a guided wave which propagates along the periodic obstacles. And we know that the guided waves exist below the cutoff frequencies, which means that when the frequency is outside the radiation continuum spectrum. But the bound state is continuum is characterized by its opposite case. So the periodic system supports the guided waves even in the radiation continuum. So this is the bound state in the continuum. And we want to realize such a very exceptional bound state by using topology optimization. And this is a formulation of the system. And we consider the two-dimensional time-harmonic system. So the governing equation is Helmholtz equation. And this is a periodic problem. So we have a Bloch condition or Floquet condition, and its wave number is denoted by beta, and the lattice vector is denoted by A. And we solve this boundary value problem by using the multiple scattering theory as before. And the problem is now formulated that what we want to do is we want to find pairs of the frequency and the wave number beta, such that there exists a non-trivial solution of the periodic boundary value problem. And this is converted to the standard linear algebraic problem by using the multiple scattering theory. And I'm not going into details about this formulation, but we can see that the problem is now to find the frequency omega and the wave number beta that satisfy this simple linear equation. Okay, so the bound state is now characterized that both the frequency and the wave numbers are real. And we realize such properties by using the topology optimization. Okay, so now this is the result. And this is the standard case. So we have a circular obstacles periodic in the horizontal direction. And this is the bound diagram of the periodic obstacles. So the right horizontal axis is a wave number, and the vertical axis is the frequency. And we focus on this point this eigenvalue, and we can see that this eigenvalue stands for the leaky mode, and we optimize by using optimize the shape of unit structure by using topology optimization to minimize the imaginary part of the wave number. And we can see that this is the optimized unit structure, and this is the optimized guided mode. You can see that the guided mode is perfectly confined around in the vicinity of the periodic structure. Okay, so this is a result of the optimization, and this is a conclusion. Okay, so maybe time is up. Okay, thank you very much.
Yeah, thank you very much for a very excellent presentation. So we have time for questions. So please raise your hands. If you have a question or two. All right, can I start maybe with
Harold has a question. I mean,
oh sorry Harold, sorry.
No worries, I started
yes,
slow with the hand. Nice talk, thank you very much. I was wondering on basically page 9 and 6 and 9, when you had these rods there was some kind of fourfold symmetry to this. Was this on the page before that? I think on page 6, that was kind of a fourfold symmetry there of these rods, or do you make some implicit symmetric arguments for how you position the rods, or is this completely free?
No, this is not the symmetry is not assumed in these systems.
Oh, okay.
Yeah.
But on page 9, you basically had a different number of rods per circle. Is this?
Yeah. So the system is not perfectly symmetric.
Okay.
But in such cases, also, so as you mentioned that this system is not perfectly symmetric, but however, the result is almost invariant under the change of the incident angle. So this is not symmetric, but the scattering is almost symmetric.
Okay, great, thank you.
Actually, this is very similar to my question, so I'm going to ask it. So if you go back to slide 6, so just looking at the geometry, so how can you basically change the geometry when you have, let's say, different frequencies, wave frequencies, which are basically interacting with your structure? So basically, how to change the configuration dimensions based on the incident wave frequency?
Yeah, I think that is not mentioned in this article. So the operating frequency is fixed, and they optimize the structure. Exactly. So we have to optimize the shape by if we change the operating frequency.
And is it trivial, or is it a kind of limitations?
Yeah, I think it's a limitation. This applies for my proposed system. Yeah, this only works for the very specific operating frequency. Yeah, that is the limitation of the proposed system.
Right. I see. Yeah. Okay, we have time maybe for another question.
Marie,
sorry. I'm blind today. Yeah. Sorry. Yeah.
I just have a quick question. First, thank you for your talk. And it's more toward the end when you have those this example with the left wave and the right waves coming in. Perhaps you'd say something about it, but I just for clarity again. So it seems that everything is symmetric, and I don't remember. So I don't know what was the reason that in one sense you have a perfect cloaking, and the other one it definitely doesn't make any cloaking. It was
so the geometry is symmetric, but its material distribution is not symmetric. Okay, so the left part has the gain, lossy median, and the right part is the gain median. So that's why the scattering property is asymmetric with respect to the
Okay, no, I think
horizontal direction.
yes, I see that. Okay, so the material is not symmetric here. Okay.
Yes.
And have you checked
Okay.
what happened if you actually come from from the top of the bottom? Because it's what would
Okay.
happen?
So, okay, this is the figure when the incident direction is changes from 0 to 360 degree. So this is the left case. This is the case of the plane wave is incident from left, and the 180 is the right incident case. And if we change the incident direction, and then the perfect cloaking is only achieved for the left propagating case.